In question 8, we're not finding the composition, but we are operating on two functions. We're going to find the difference, the product, and the quotient of two functions. We're going to state the domain. I omitted the directions where you do not have to state the range of each function on your quiz, so that is not something you have to be concerned with, at least in the immediate future. So what we're going to do is we're first going to find the difference of function f and g, which means we take function f, which is x squared plus 5x plus 6, and we simply subtract function g, which is x plus 2. Making sure that I put those in parentheses so I don't forget to distribute. So x squared plus 5x plus 6. Before I collect like terms, I need to distribute. And now I can collect my like terms, x squared plus 4x, and then plus 4. This is the difference of f and g, the function, f minus g. The domain restriction, well, in this case, there is no restriction. It's a quadratic equation. A quadratic equation is a U-shape, and there are no gaps, omissions, vertical asymptotes. So it is defined for all numbers. So since it's defined in all real numbers, and we're putting them in interval notation, our domain is from negative infinity to positive infinity. So next we're going to do the operation of multiplication. So now we're going to find f times g of x, which means I'm going to take function f, which is x squared plus 5x plus 6, and I'll multiply it times x plus 2. Multiplication should imply that we're going to have to distribute, and we're going to have to use a multiple distributive property here. What I'm going to do is I'm going to show distributing from right to left. So I'm going to take x times x squared and get an x cubed, and x times 5x, which is 5x squared, and x times 6, which is 6x. And I'm going to distribute through with a 2. So plus 2x squared. I'm going to put my like terms underneath each other. And 2 times 5x is 10x, and then plus 12. I'm going to collect the like terms. So x cubed plus 7x squared plus 16x plus 12 is the product of f and g, the two functions f and g. So this is my composite function. Now what I want to do, or not my composite, my product function, examine the domain. This is a cubic function. Again, cubic functions are some type of an S shape, and they are continuous in the entire interval of real numbers. So your domain is from a negative infinity to infinity. The last one we're going to do is we have this one where we have a quotient or a division problem. So take function f divided by function g, which means it's got to be an x squared plus 5x plus 6 divided by x plus 2. So in order to divide, we want to make sure that we restrict any domain values that will cause us to divide by 0. So this is a red flag immediately. We want to make sure that x plus 2 does not equal 0 since it's undefined. So that means we do not want x to be a negative 2. So part of the problem has been solved where we can use all real numbers except negative 2. So just finishing up on that domain idea, then our domain would be in interval notation, negative infinity to 2, negative 2. Union that with negative 2 to infinity. I want to make an analogy here with this division that we have right now. We always want to try to put division problems in simplest form. And this is going to be a very simplistic example, but 6 divided by 3. If we see this, we wouldn't want to leave it that way. We'd want to remove common factors. So 6 is 3 times 2 divided by 3. We want to remove the common factor and more simply write our solution is just 2. The same is true with these polynomial equations, and this is a rational bit with a polynomial and another polynomial. We want to see if there's a common factor of x plus 2 on the top and the bottom. So on the top, I won't recognize if it has any common factors until I put it in factored form. So really becomes a problem where we're going to grab the common factors and factor this x squared plus 5x plus 6, which trinomials, if factorable, factor to two binomials. X squared is x and x. Signs have to be the same sign. They both better be positive, so plus and plus. Factors of 6 that will give you a 5 are 2 and 3. And lo and behold, what we see here is a common factor of x plus 2. These can be reduced just as we reduce the common factors of 3, and we end up with a simplified version for our quotient function of f divided by g of x, which equals to x plus 3. Here is our quotient function. It has some restrictions on it. You can never use -2 as an input because it wasn't allowed before we simplified. We have division by 0. The nice thing about finding those removable spots, and what we should know from previous lessons, is that this represents a hole in your graph. It's a removable discontinuity, and we can just get a simple graph of this, what looked like a very complicated graph. It's just a linear graph of up 3, slope of up 1, right 1, up 1, right 1. So here's the graph of our quotient function, but it has a hole in the graph at -1, -2, and it should have an input at a -2. So basically the graph that we look at would be the blue graph with a hole in -2. Since -2 is not allowed, that means a -2 plus 3, 1 as an output can never be achieved. So that's what this is saying. At 1, we can never have an output. There's a hole there. Now that's above and beyond. This part of the graph is above and beyond what I asked, but I wanted to connect it with some ideas of holes that are in your graphs. So that is on the difference, product, and quotient of two functions.